Okay, good evening, everyone, and welcome to our very special live stream this evening. My name is Joe Wheelock, and I'm coming to you live from the McDonald Observatory here in far west Texas. Now, tonight we're going to talk about a technique astronomers use called spectroscopy. This is a lot less painful than it sounds. It's a technique that allows us to discover many interesting things about the universe that we live in. Now, if you've been to, now, we'd like to know if where you're all from tonight, so we can see where everybody's joining us from tonight for our program. Now, the first part of the program tonight, we'll talk about this technique and how it is used in astronomy. Now, we have planned to show you various spectra of some different objects with our telescopes, or one of our telescopes. Unfortunately, the weather is not very good tonight at the observatory, and we'll get to what's going on with the weather here in just a few minutes. And I live and work here at McDonald Observatory. I've been here for over 22 years. Now, before I came here, I did public outreach with an astronomy club, also worked in a planetarium, and I've also had courses in chemistry and physics and mathematics, but my real passion has always been astronomy. Now, if you have any questions at any point during the program, feel free and post those questions in the chat. We have moderators standing by to answer any questions you may have, and we'll take questions too at the end of the program. Now, I want to introduce co-hosts tonight. We have Saul Rivera and Stephen Hummel. You may recognize them from some previous live streams. So Saul and Stephen.
Yeah, so hello, my name is Saul Rivera. I am also live and work here at the McDonald Observatory as a public affairs specialist. So I do like the tours, live streams like this, and other similar activities and projects. I haven't been here as long, only been here for about 2.5 years. But still the same, it's really fun to be out here.
Thanks, and yeah, I'm Stephen Hummel. I'm our dark sky specialist, so most of my job here at the observatory is working with the surrounding communities and the public to engage about preserving our night sky. But I also do public programs like this and star parties and other things. And like Joe and Saul, I live on site. We're all neighbors. Nice little community here. But yeah, tonight I will be hopefully operating this telescope behind us. Well, as Joe mentioned a minute ago, the weather tonight doesn't look super promising. You can't hear it through my mic probably because of the noise filtering technology. But if I take my headphones off, I am deafened by the wind around the dome I'm in right now. It's so windy that it's not safe to open the dome. Gusts probably in the neighborhood of 50 to 70 miles per hour. So unfortunately, it's not likely we're going to be opening the telescope to have live views through it, but we do have some prepared views from last night too. So, Joe, if you would.
Okay, that's all you have for us? All right. All right, so thanks, Saul and Stephen. We'll see you later on during the program. Well, let's go ahead and let's talk about this technique here, spectroscopy. And before we do that, though, I want to show you a map of where we're located here in far west Texas, out here in the Davis Mountains, region. We're pretty much in the middle of nowhere. And you saw Stephen in the dome a few minutes ago. Here is a picture of our visitor center and telescope park, and the arrow shows you where the dome is located. Now, when you saw him in the dome, he's using an infrared camera. So that's why things look kind of pinkish when you saw him in the dome. I want to show you a picture of the telescope that we plan to use, may still be using, but unlikely because of the weather. But here is a picture of that telescope. This is a 16-inch telescope, and that refers to the diameter of the mirror. Most large telescopes, they use mirrors to gather the light. Now, the telescope, it is on a mounting that tracks an object across the sky, compensating for the Earth's rotation. The telescope is also computer controlled. Now the picture, it's lit up with red lights because red light helps you preserve your night vision, your dark adaptation. You know, your eyes can take time to adapt to the dark once you leave a lighted room, maybe 30 minutes or so or more. So that's why we typically use the red lights. All right, so this technique here, what is spectroscopy? Spectroscopy. Now, whenever we take light and we pass it through a glass prism, it breaks up it into colors, like colors in the rainbow. Now, we don't usually use prisms in our equipment. We use a similar device called a diffraction grating. Diffraction gratings have thousands of lines that are etched into these diffraction gratings, perform the same function as a glass prism. Now, the fact that light is made up, white light is made up of colors, that was demonstrated by Sir Isaac Newton back in 1666 from the Newtonian telescope. He also invented the Newtonian telescope. If you have a telescope with an eyepiece on the side of the telescope, that would be a Newtonian telescope. In fact, I have a couple of Newtonian telescopes myself, and I built Newtonian telescopes too in the past. So he's a very important man in astronomy. All right, so when we see a rainbow, like in this picture here, what you're seeing is just a spectrum of the sun. You have sunlight passing through water droplets, making a spectrum of the sun. Or if you ever played with a lawn sprinkler, you might see if the sunlight's at the right angle, you would see that you would make a little rainbow from the lawn sprinkler. Now, there is always a certain order to the colors of the spectrum, and there is a mnemonic device you can use to memorize the order of the colors of the spectrum. If you know what that is, share that with us in the chat. Let's see if we have any answers here for that. I'll pop it up here in a minute. I'm not seeing any. Okay, kind of silence here in the chat. So let me show you what it is. Rory G. Biv. Rory G. Biv. So what does that mean, Rory G. Biv? Let's talk about that here. So here we have a picture, artist picture of a rainbow. So here are the orders, the colors of the spectrum. We have red, orange, yellow, green, blue, indigo, and violet. So now, does anybody know any other ways to memorize the order of the colors? Anybody know that? I see. Okay, here's some chatter here. I'm looking at the chat here, and I'm seeing kind of crickets here on that in the chat. So, well, I'll tell you some that one that I've heard. If anybody is anybody here perhaps from England tonight? England, maybe across the pond there. Nobody from England, maybe. Okay, well, all right. Well, the versions I've heard of it are Richard of York gained or gave battles in vain for the orders of the colors of the continuous spectrum. Okay, well, moving along here then. So we have three basic types of spectra. We have a continuous spectrum. If you have a solid heated to a very high temperature, or a gas under a high temperature and a high pressure, it will exhibit a continuous spectrum. We also have absorption spectra. You could have starlight passing through a cloud of gas and dust in space. That's called a nebula. And some of this light could be absorbed or blocked. Sometimes you could have the starlight also passing through the same nebula, and it could excite the atoms of the nebula. That is called an emission spectrum, sometimes called a bright line spectrum. Now let's see here. There are three different things. There are three main things you can determine by using a spectroscopy here. So let's see here. Let's talk about. Let's see here. Let's see. Oh, here we go. I want to have a question for you first. Let's see. Let's get this here. So we have compositions. Compositions. What are stars and planets made of? Then we have temperatures. You know, how hot are stars or cold stars? And then we also have motions of objects. So we'll talk about these in detail now. So do you remember the name of that chart that shows all of the elements? What's the name of that chart? Remember the name of that chart? Anybody remember that? Give me a minute here to think about that one. Not seeing any answers there. Let me show it to you. That's called the periodic table. Periodic table. Now, another question for you. Do you know how many naturally occurring elements there are in nature, naturally occurring elements? Anybody remember that from your chemistry or physics classes, perhaps? Don't worry, folks, there isn't going to be a test. No test. Don't see any answers coming in the chat. Give it a couple more seconds here, a minute or so. 118. Steve Ganaway. Lower 8. Let's see, it's between 8 and 118. I can tell you that. I see 103. That's close. You're getting in the right. You're getting in the right track here. You're pretty close. Well, okay. Got a lot of good guesses here in the chat. 76, 92. There are 92 naturally occurring elements. So who was closest here? Looks like we had 107's close. 96. Yeah, Denise Welch, you said here 96. Yeah, let's see. Where was your? Oops, that's the wrong one. Let's try this one here. So you were close. Yeah, 92. Here we go. You had it right here. Let's get this right here. Yeah, you're exactly right. 92. Let's see, that's Hamish. Yeah, 92. So there are 92 naturally occurring elements. So compositions is the one thing we can talk about. Okay, next we can learn about temperatures. Temperatures of objects. Now, it works kind of differently than how you think it would work. In science, you know, the red stars are cool, blue stars are hot. Think of it like this. Think of a blue flame on a gas stove. Another way to think about it, I like to go camping a lot. When I was a kid, you know, I go camping a lot, still do some when I can. And if we had a really hot campfire burning, really hot campfire, sometimes you might see perhaps a green flames in the campfire. So that's blue stars are hot, red stars are the cooler stars. Now we classify stars not only by their temperatures, but also by their, their sizes. In fact, there is a diagram called the Hertzsprung-Russell, or HR diagram. And this diagram, there's an American astronomer, Annie Jump Cannon. She was instrumental in cataloging a lot of stars to help with this this Hertzsprung-Russell diagram on here. So, all right, so we had compositions and temperatures. And what do we have next here? Motions of objects. I'm sure you've heard of the Doppler effect. I want to play for you a little audio clip of an example of the Doppler shift. Here we go. Okay, so in that clip, we had a car coming at you, honking its horn. So as the car is coming at you, honking its horn, it had a high pitch because the sound waves there bunched together. As the car went by you, the sound waves had a low pitch because they were spread apart. So that is where we got this as the car went by. Pitch is to sound, what color is to light. So here's what we can learn by using the Doppler effect, different things. We can learn about exoplanets, figuring out, whoops, jumped a slide there, figure out whether we can have, whether or not a star has a planet orbiting around it. So as a star, as a planet would orbit around a star, it would tug in it slightly. And this would cause the star to wobble a bit. From that wobbling, we can figure out the size of the planet, orbital period, many different things. And there are stars, about half the stars in the sky have one or more companions. We call these stars binary stars. Now, some binary stars are so close together, we cannot separate them with a telescope. We would need a spectroscope to do this. So what we would do is take a spectrum of the star, and what you would see are two sets of lines superimposed over each other. And as the stars orbit around each other, those lines, like in this little animation here, would shift back and forth. So from that shifting, we can figure out, again, the size of the stars, orbital period, many different things. So now you can see how this tool in astronomy, the spectroscopy, it's very important tool that we use. Okay, let's shift over now to Stephen. And Stephen, how is the weather out in the dome?
Well, Joe, the weather has not improved. It is still very windy. I can feel the dome rattling around a bit in the wind. It's a little unnerving. And our measurements show it is still too dusty to really be safe at opening the dome. And on top of that, it's also gotten even cloudier. So even if weather was
that's
good,
unfortunate.
Yeah, clouds would be blocking everything else. But do have some pre-prepared views if you are ready for them, Joe. Or
yeah, in fact, let me show the group something here tonight. We're going to look at it. Well, we're going to start off here in a minute, and we're going to look at the spectra of several different objects, different stars and some other things. In fact, we took some pictures of these last night. What I want to show you first is a map of the sky of where two of these stars are located. And then we'll switch over to Saul, and he'll talk about a couple of these stars. So let's go ahead and let's stop the screen here. Now give me a second here, and I'm going to share with you a map of the sky. And that didn't work. Let's try that again. It helps if you if you click share. It's lost permission. Okay. That's weird. Okay. I never have technical problems, you know that.
Well,
So,
if you want me to point out where our first object is, I can also do that. If
yeah,
you'd
if you
like.
could do that, that would be great.
Okay, yeah, let me do that for you. Okie dokie. So, our first object tonight, I'm going to share my screen here. This is the software I use to control the telescope behind me. Now, currently the telescope is pointed over where this yellow dot is because I have it in a parked position since we're not actually using it. But where I have this green laser pointer is pointed, the first star we're going to kind of take a closer look at tonight. It's a star some of you are probably familiar with. It's Betelgeuse is its name. Betelgeuse, not spelled at all how it sounds. And it is kind of the shoulder of Orion, his left shoulder or right shoulder, depending on how you think about it, if he's facing you or facing away. But one of his shoulders, it's just above Orion's belt. Very, very obvious group of stars there, part of Orion. So that's the first object we're going to take a look at. At the moment, it's located straight south. It's a very bright star, and even if you're in a big city, you probably can still find this one, as well as some of the other ones we're looking at tonight. So for a telescope like this, this is easy, super easy target, but it also has a very impressive spectrum. But I'm going to hand it to Saul, talk a little bit more about Betelgeuse itself before we go to a view of it, previously taken from last night.
All right, thank you, Stephen. Yeah, so let's learn more about the shoulder of Orion. Betelgeuse, or I was going to say Betelgeuse, don't say a name 3 times, bad things may happen, is a super red giant that's about 650 light years away from us. And this star is huge. As you can see from my screen here, you have a comparison of different stars. You have Sirius, Rigel, Aldebaran. The large red thing in the background is Betelgeuse. And a little bit of yellow dot to the top left, the one with the arrow pointing to the sun, that's the sun. This star is about 900 times larger in terms of radius than our sun. And actually, it's going to go supernova very soon. It's going to go supernova literally any second. So I'd be looking out the window if there were no clouds. Or within the next 100,000 years. So we got a good leeway going on. Or maybe it already did blow up, go supernova, and we haven't seen the light from the explosion yet. When the light from the explosion does reach us, though, it's estimated that it will be so bright, it'll outshine the full moon for about an entire month. Or if it happens during the summer, it will be visible during the daytime. So extremely large star, extremely close to us, and with lots of cool stuff going on. And then what we're going to see is how actually, so we saw the continuous spectrum from Joe and the absorption lines and the emission lines. And now we're going to see how that actually looks like looking at an actual star. And I think, do you have it ready, Stephen? There it is.
Yeah, thank you, Saul. So this is a spectra that I took last night. And what I mean by that is you see the star is on the right. That's Betelgeuse right there. And on the left, we have 2 multicolored lines. So in front of the camera that I used to take this picture, I inserted a diffraction grating, which Joe mentioned earlier. It's taking that light and splitting it apart into its component colors. So it is acting as our spectroscope or spectrograph in this case. So the first line you see here, this group, this is identical to the line you see here, but this one, although it's basically the same, they're both from Betelgeuse, it is more spread out, but also fainter. So we can see more details in there. But if we look carefully at this spectrum here of Betelgeuse, you can see, there's colors. Obviously, we have red and yellow and green and blue. But notice that there is a lot less blue than there is red. And that's, of course, because Betelgeuse is a red supergiant. It's just a red colored star. And that, of course, tells you the temperature. So the hotter the star, the more blue it will have. The cooler, the more red. Now, you can get a rough idea of that just by looking at the star and, overall what color it is. But if you really wanted to be precise and get a better idea of exactly how hot a star is, you would really be better served with a spectrum, because that kind of breaks it all out into its proportions. But also note that if you look carefully, especially kind of right around here, a little bit around here, it gets dimmer. It's not just smoothly transitioning from one color to the next. It's dimmer because those are absorption lines. So again, Joe mentioned earlier. What that tells us is there's something in front of the star that is blocking those particular colors of light. And each element and molecule has its own unique pattern of light it blocks. So based on the pattern of light here, we can figure out what is in front of or surrounding or on the surface of that star. And in this case, it is actually a molecule, titanium oxide. This titanium oxide absorbs light, particularly in a kind of red color and kind of the green color and some other lines as well. That's actually kind of unusual. If you look at the spectra of most stars, you will find absorption or emission lines of certain elements like hydrogen, helium, and other things. But you don't often find molecules. The only way you can have a molecule around a star is if that star isn't really all that hot. And Betelgeuse is just cool enough that molecules can still form without just being instantly destroyed and vaporized and broken down into their component elements again. So it's kind of almost like a soot you can think of. Betelgeuse is surrounded in this kind of cloudy soot-like substance, and that is what is causing those bands. It's also what caused Betelgeuse to dim down a little bit a little over a year ago now, maybe a couple of years. You may have heard about that in the news. Betelgeuse got much dimmer. It's because that cloud of soot around it got much thicker. Yeah, I see another question from here from Stephen Yanagasawa. How long of an exposure? In this case, this was about a quarter of a second. So very, very short. I could do less because this is a bright target. But depending on your target, the dimmer it is, the longer you're going to go. So it is not uncommon here at McDonald Observatory for research telescopes to spend multiple dozens of hours on a really faint target to get a spectra of it. But okay, that is Betelgeuse. I'm gonna hand it back to y'all.
Yeah, thank you, Stephen. Yeah, so our next star is Rigel. So Rigel is also in the constellation of Orion, but instead of being one of Orion's shoulders, it's one of Orion's feet. And it is the brightest star of Orion. So if you can't see Betelgeuse for some reason, you'll definitely see Rigel. Or if it's just super cloudy like tonight, you won't be able to see either. But Rigel is also a supergiant, though not nearly as large as Betelgeuse. So kind of going back to my previous slide so you can see that comparison. Still a lot bigger than our sun, but not nearly as big as Betelgeuse. It's actually only about 80 times larger than the sun in terms of radius instead of Betelgeuse's almost 900. And it's about 860 light years away. And despite being further away, it's still brighter than Betelgeuse. So kind of with astronomy, or kind of like as we saw the Hertz-Russell diagram, a star's color can show us its temperature. Betelgeuse was a cold star, very low, kind of cooler. Rigel's a bright blue star, a lot more energetic, a lot harder. So I have a question for y'all. So with Betelgeuse, we saw how the reading of the spectrum was for a cool red star. Now, how about we look at a star that's a bright, hot, young blue star? What do you think is going to be different in the reading? Feel free to drop your guesses in the chat of what do you think will be different? Will it look the same? Will it look different? Will there be not only just with the lines, but just the way the band looks like in its own? Let's see.
It's a good
And
question. Yeah.
yeah, as people submit their guesses, Stephen, we got Rigel already.
We do have Rigel ready. Yeah. So when we see Rigel, of course, I'm going to reveal the answer to that. But here we go. So
Oh,
this is an
yes.
yeah.
So sorry. I'll say, want to
There
point
we
out
go.
some good guesses, like colors in reverse, more blue, more linear. Well, here's the answer.
Here you go. Yeah. So yeah, it's more blue. If you look at the blue end here, you'll notice that you can trace it all the way out deep into the almost violet. And in fact, a really massive star like this would also emit a lot of ultraviolet light, which is beyond the detection range of this camera in this system. But it would actually continue on into the ultraviolet as well. There's still definitely red in there, but a nice bit of blue too. I also wanted to add that Joe mentioned earlier, many of the stars you see in the sky have companions. Rigel is an example. It is actually a multiple star system, and it's got one of the members right there, just above it, much fainter, almost hiding in the glare of Rigel itself. But we're not really picking up the spectrum here. I wasn't exposing for it. So it would be there if I were to take a longer exposure, but I didn't in this case. But notice also that those bands that we saw before from titanium oxide and Betelgeuse, those kind of missing parts, aren't really here anymore. It's much more continual. You may argue there's a little bit of variation in some of it, and with a very powerful spectroscope, you can pick out absorption lines, but they really are much more subtle here. So you can't really pick them out. Much more linear kind of appearance to the spectrum overall. So let's see, we had some questions here. Lara Epsilon asks, when you take the spectrum, do you focus the light on the diffraction grating or merely insert the diffraction grating in the light path? I am focusing in this case on the spectrum. How sharp it is depends on how stable our atmosphere is in this case. But I am focusing on the spectrum. So the star on the right is actually a little out of focus because that's not what we're really looking for. We're looking for the spectrum on the left, and that's what I focused for. All right. So that's about it for Rigel. All right. So Joe, you want to take it away?
All right. Oh, and the question did come in. So with the focus of spectrum, would that also cause from there to be the yellow not as visible, or what would cause that?
The yellow is visible here. It's just subtle. In this case, it's just yellow kind of blends a little bit into green and red, and so it's harder to discern. But the yellow portion is just sort of a short transition between the two, but it's there. It's there if you look for it.
Okay.
Yeah.
Thank you. Yeah. So first we saw Betelgeuse, an old red supergiant. Then we saw Rigel, a very energetic blue supergiant. Now, how about we look for one that's in between, at Capella? So Capella's in the constellation of, I'm probably botching the name, Auriga, which is the charioteer, and it's the brightest star in there. So kind of want to start thinking, and if you want, you can put in your guesses as to what the spectrum of the star will look like. So with a cool red star, it seemed like there was fading into blue. With Rigel, there was more vibrance in the violet, even going to the ultraviolet. What for a star kind of closer to our sun look like? So Capella is about 3 times more massive than the sun, about 43 light years away, so a lot closer than Betelgeuse and Rigel. And also, it's actually a quadruple system. So while Rigel's one binary pair, Capella's actually 2 binary pairs, all kind of circling each other. So now we have that other little thing added in. As Joe kind of showed earlier, we can look at the star spectrum and detect these wobbles to find out if there are more stars in the system. Kind of using this technique, they figure out multi-star systems such as Capella, of saying, hey, are these 2 stars just close to each other, or are they actually interfering with one another? So now, as kind of y'all have the guesses now of what the spectrum for a star like Capella is, what about if you throw in what do you think if there will be any differences right away of it being a multi-star system? Let's see, some people were asking is redshift to Rigel. Yep, Rigel would have kind of a bit of a shift as it gets pulled in and out, as it gets pulled away and closer to us. And I think we're ready to show the live view of Capella.
All right. So here we have, well, not live again. It's last night, but
Yeah.
it was live last night. So again, if we were to use the telescope, this is almost exactly what we would be seeing live. This is just taken last night. But this is Capella, and it is a little more yellow of a star, kind of in between, as you mentioned. And so there is less blue than there was before. That's for sure. But yeah, since this is a multiple star system, we are actually getting the spectrum of several stars sort of overlapping. However, it's usually dominated by the brightest member of the star system, and so that's really what we see is Capella A, so to speak. But yeah, if you were to look at multiple star systems, you have to be kind of careful at first to not get confused, because if you have two stars right next to each other and they're kind of within the same region right here, you're going to see the spectrum of both simultaneously kind of overlapping, interfering with each other a bit. And so astronomers have to be careful to tease those apart and not get too confused. And the way you could tease those apart is because as one of those stars in the pair is moving towards you, the lines from that star will be shifted to the blue. And as the star that's moving away goes away, those lines from that star would be shifted to the red. So if you have two overlapping, some of the lines may be moving and not the other. But yeah, you would need a really powerful spectrograph, like some of the ones we have on our research telescopes, to really see all those effects. But in this case, you can definitely see the color is yellow, and there's just kind of an even amount of light across red, green, and blue there. All right. Let's see. Have any questions? No?
I see one from Thomas and Amelia Grimstad. Any planets around these stars? So from what we've seen, Capella doesn't really have any. Betelgeuse doesn't really have any. But Rigel does have a number of planets. And actually, it's really cool that you asked this, because our next target is actually a planet. So we saw how spectrum lines look for stars. Now, how about if we do something like a planet, such as Uranus? And despite all the jokes, that is how that planet's name is said. Uranus, as you know, probably know, is a planet in our solar system, about 1.18 billion miles away from the sun. It takes about 84 Earth years to go around once, orbit the sun once, about 17 hours to complete one rotation. Extremely cold, so about 357 degrees Fahrenheit below zero. And actually, one of its moons, Miranda, was discovered here at the McDonald Observatory on our 82-inch telescope about 74 years ago. So happy birthday to the discovery of the moon, Miranda. So some other cool things about Uranus is Uranus kind of actually spins on its side. And it kind of goes like a bowling ball through space. And also, so in this view, it actually has a ring system, just that it's very hard to detect. So in these images, both are Uranus, but the one on the top is actually an infrared view of Uranus, so you can more easily see the ring and other activity going on. And yeah, then so now that we have a planet in position, what do you want? You can drop your guess in the chat of if there will be any differences of looking at a planet versus looking at a star with our diffraction grating.
And I'll add a clue there. When we look at stars, those stars are emitting their own light. But Uranus and other planets aren't. They're just reflecting sunlight. So that's gonna mess with our spectrum a bit. What do you think we're gonna see? right. Well, thank you also for pronouncing it correctly, so Uranus. But it's still better than the original name, historic name for Uranus, which was the Georgian star. It's an improvement, named after
Yeah.
King George.
Oh yeah, I almost forgot about that.
I remember that.
Yeah. Yeah, thankfully we didn't stick with that.
Yeah.
All right. So we got some guesses here. Yeah, it's going to be a reflection of sunlight. We got someone saying it's going to be much cooler. Someone saying have absorption lines.
Absorption
So
lines.
yeah, very good. So here is the spectrum of Uranus. And there's Uranus on the right. You can see in this case, there are definite absorption lines or bands, if they're really thick is what we call them. So Uranus is just, reflecting sunlight. So basically what we're seeing then is the spectrum of the sun, but Uranus doesn't reflect all of the light equally. Uranus is going to reflect some light more than others, depending on its composition, and it's going to absorb certain colors of light, also depending on its composition. So overall, Uranus has a kind of bluish tinge to it, kind of a really subtle cyan, blue-green color to it, or pale blue. So that is because of its composition and outer layer of clouds, but it also is absorbing in certain lines, primarily from methane that is within those clouds. So what you're seeing then is the signature of methane there within the outer layers, absorbing certain bands of light. It's got quite a lot of it, so the signature is very strong. So when we look at other planets, we can see similar things. At the moment, there aren't any other planets in the sky. There weren't, last night either when we took this. But if you look at the spectra, say, of Jupiter, you would have a very different composition to it. And what do you think you would see if you looked at the Earth from far away? What would be absorbing or reflecting light on the Earth? Yeah. It'll probably be water, since that's most of what the Earth is covered with, and we have a lot of water vapor in the air. So if you look at the spectra of the Earth from far away, you would see signs of water vapor as well as other things. So with that knowledge, then we can look at other planets and figure out what's the atmosphere like without actually having to go there. And hopefully we can really start to apply that in more detail to planets orbiting other stars. Very tricky technique to do that, but with this knowledge, we can do it. All right. I also see people saying oxygen in the comments. Yeah, oxygen would be definitely, you would see the signature of oxygen in the Earth as well. You'd see the signature of many things, but water vapor is a particularly prominent one. Alrighty, Saul, Joe, back to you guys.
Okay,
All
thanks,
right.
Stephen. All right.
Yeah, so we got to look at sorry. We got to look at a star. We got to look at a planet. But when we look at something completely different, well, we look at a different type of object we call a nebula. So nebula is basically the big ball of gas and dust that is either giving birth to new stars or what's are left over when the star dies. We're looking at the latter, what we call a planetary nebula. Or more specifically, the one we're looking at tonight is NGC 2392. Which is a very fun name, it does have actually some other names. The one we like for here that was given by another live stream is the Dandelion Nebula. And I really like how that one sounded like. So like Planetary Nebula is what's left over when a low mass star, kind of like our sun, dies. As it dies, it pushes away the outer layers until leaving behind its core, which we call a white dwarf star. The Dandelion Nebula is about 5,000 light years away, about 1.5 light years across, and from our estimates died about 10,000 years ago. And the reason it's called planetary is that when astronomers first saw these objects, they thought they found the areas where planets were born. We now know that isn't true anymore, but the name kind of stuck, which is kind of a common thing in astronomy. So feel free to drop in the chat what you think we'll see looking at the spectrum of a planetary nebula. So we saw how it looked like when the star was still alive and going. We saw one of the star close to death, but how will it look like for the actual remnants of a dead star? Seeing people starting to drop their guesses in the chat.
Yeah, I'll address a few questions while we're waiting for people to answer that one. But Gary Post asked if the James Webb Space Telescope is capable of looking at exoplanets' atmospheres. If the planet is in the right position relative to its star and our line of sight, then yes. So typically what will happen to obtain the most detailed spectrum of a exoplanet's atmosphere is that planet will cross directly in front of our line of sight of that star. So you'd see the star get dimmer overall, but if that planet has a thick atmosphere, the light will pass through that atmosphere a little bit, and that'll change the spectrum a little bit. And therefore, we can detect the composition of an exoplanet's atmosphere. So we can do that already with current technology, but the James Webb will be capable of doing that even better. And it may also be able to determine it by other means. It's a little more tricky. All right, so we got some guesses here on what this is going to look like. More to the red end, some absorption lines. So yeah, good guesses. This is probably gonna throw some people for a loop because this one is honestly a pretty strange looking one. Are you ready? All right, here's the spectrum of the Dandelion Nebula, NGC 2392. So I actually have several star spectra in here. We have a star on the top, which I kind of just included because it was nearby the Eskimo Nebula over here. And it makes for a nice comparison. Pretty standard star, all things considered. It's got quite a bit of purple in it, so it's probably pretty hot, this one. But on the nebula, let's take this apart just a little bit. We have a spectrum of the nebula, which is an extended object, not just a point source. And we have a spectrum of the star in the middle of it. And the star in the middle of it, if you follow over, is this central line. And the nebula's spectrum is actually not an extended band, as you would expect, but just two distinct images. One that's teal, kind of blue-green, and another that's red. And that's it. 1, 2. And we have, again, a continual spectrum of the star in the middle. So earlier on, Joe talked about the three kinds of spectra that generally there are. There's continuous, which is what we have in the star up top. Absorption, we saw that in Betelgeuse and Uranus, where it's absorbing particular parts of the light, so there's gaps in the continuum. And lastly, there's emission. And emission is basically just distinct lines with nothing in between them. And that's what we have here. And this happens typically because the gas is fluorescing. So we know the composition of this object because of that spectrum. Each element has its own unique signature. And if you get different gases excited, then they'll emit very particular lines, like a neon sign. Pass a current through a neon sign, the neon glows very particular colors. In this case, what is glowing for the green color is mostly oxygen. Maybe a little bit of helium in there too. It's really close color when it's excited, but primarily this is from oxygen, ionized oxygen. Now, this is something that we wouldn't see here on Earth. This is a reaction that can only occur in the near vacuum of space. So this cloud of oxygen is glowing from the heat of the star in the middle of the cloud that's dying. Then next up, we have hydrogen. It's a deep red. Astronomers call this particular red emission hydrogen alpha. It's a very, very common color to see. When you look at pictures of other nebulae and things, you'll often see them are dominated by red because they are mostly made of hydrogen, and that hydrogen is fluorescing or glowing from the heat and energy of stars nearby. So same thing here. We have hydrogen and oxygen, both generated and pushed away by that dying star in the middle, and now they are still being energized from the heat and energy of that star. So yeah, kind of a lot going on there. I think it's pretty neat to have a kind of double ghostly image. I think it's one of the prettier spectra out there.
Yeah, that's super cool. I actually, when I first saw it, I thought it was like some weird glare from like the cloud. I didn't realize it was actually doing its own reading.
Yeah, the cloud itself is emitting the light you're seeing it from it. Yeah. So if you go back to the picture of before, you can appreciate it a little better. Like, so you're seeing again the spectra of that cloud around it, separated into two colors, kind of orangey red and then blue, and then bluish light in the middle. That's actually a kind of false color view from the Hubble there. In reality, is when you actually look at it in a big telescope, it looks kind of greenish, kind of blue green. Yeah.
Yeah, that's super cool.
All right. Well, that's the last target we have lined up. So, thank you so much.
Yeah, thank you,
Okay.
Steven.
All right. Thanks, Stephen. Oh, I'm not a dandelion, so let me get rid of the...
We are all the Dandelion
We're not
Nebula.
dandelions tonight. Yeah. So, if it was... it's a good night to have dandelions blowing in the wind. Those are really fun. I love playing with those when I was a kid. So, all right. So let me see if I got my slides working. I was having some technical difficulties.
Yeah. Well, while you pull them up, you are more than free to start dropping questions in the chat to see which one. If you have any of the other questions that's been coming on up.
All right. So I've got something working. So we have, oops,
oh, yeah.
Not that yet. Not ready for that. Yeah, so questions. We've had some questions that were sent to our host here. And there's one from Stephen. And if you could, there's one that's good for Stephen. And if you could pull it up from Discord, Saul, it's the one, it's from Lyra Epsilon, is asking about a question about the spectrum. It says here, when you take the spectrum, do you focus the light on the diffraction grating, or merely insert the diffraction grating in the light path with the light focused on the camera plane?
Yeah, so that's one I addressed earlier. I'm focusing on the spectrum. Right. Yeah.
Mm-hmm. Yeah. One that I did see was interesting was from Gary Post. Will a high magnetic field like a magnetar change the spectrum from what we would think it would be? So, kind of, actually. So, it turns out there's something called the Z-Man effect, which is a very high magnetic field. Basically, will get your regular spectral line and basically split it, depending on like how strong the magnetic field is. So it would affect how the reading is. Though I don't really know much more about how great that will be for the entire reading. But yeah.
Yeah, that absolutely would affect the spectrum. Yeah, again, I'm not an expert on magnetars spectra. It's probably pretty complicated, but we can infer magnetic field strength of other things based on the spectrum. So I would imagine it have a pretty big effect.
Yeah. Let's see which other ones there are. Yeah, Thomas and Amelia Grimstad. Is there any kind of rain on Uranus? So there is. We like to say Uranus has kind of like diamond rain. Just like the material there, the pressure. Basically, it rains like diamonds. But it's very dangerous. I do not recommend going all the way to Uranus to try diamond hunting.
Yeah, if you're going to go out space, might as well stop at Saturn. It also rains diamonds, and it's closer and it's prettier. So
yeah.
It's carbon compressed as it falls down into the atmosphere. Very cool.
Yeah.
I see another question here from Bram, who asks, I'm guessing galaxies are fairly uniform due to the many stars, but in general might have a distinct shift. True. Yes. So if you were to take the spectrum of a galaxy, overall, you would see that the galaxy, generally, they are redshifting because they're moving away due to the expansion of the universe, dark energy, whatever that is. We don't know. But we're working on it. But so overall, the galaxy is receding away, but also galaxies are rotating. So because one side is rotating, towards you, if you're looking at it at the right angle, that side would be blue shifted, and the other side would be red shifted as it's moving away. So you would see the lines slightly shifted, one side more blue, one side more red. Very subtle, but yes, you would be able to notice a distinct shift. Now, to get a spectrum of a galaxy, you usually have to take many measurements distinctly across it to get a really good idea of what's going on there, or devise an instrument that can basically take them all at once. So it's a lot more work.
All right, let's see. If there are any other questions? Yeah, we can figure out how a galaxy is rotating using that.
Yeah, I'm not seeing any other questions. Joe, do you have anything else?
I don't have anything else to add other than I can still hear the wind howling outside. I'm sure you can too, Stephen. I don't know if you can from your place, Saul. I'm sure you can.
If it is, I probably can't hear it because of the headphones.
Yeah,
but
we
usually
some gusts here. I'm seeing some gusts here on one of our mountains at 65 miles an hour this evening. So,
yeah,
kind of living in West Texas, you kind of get used to wind and dust. You could say it's dust and the wind tonight. So,
all right.
Yeah,
Well, I think.
Yeah, go ahead.
Maybe just one more question.
One more question, okay.
Yeah. So, can light from a pulsar be captured spectrographically? Yes, it can. Yes, we have quite a few spectra of pulsars. They're pretty weird objects. But I would actually also add that the way we really know what pulsars are doesn't come mostly from visible light, but rather from radio analysis. And you can do spectroscopy outside of the visible light spectrum, including radio wavelengths, X-rays, ultraviolet, infrared. It works across basically the entire electromagnetic spectrum of light. So as usually we use radio telescopes to really study pulsars. You can actually do spectroscopy with them too. But all right, I think that's about all the time we have. So thank you so much, everybody.
Okay, so Stephen, thank you tonight for your help. I wish we would have had, better weather, but it's something that we cannot control. So I want to end by talking about what we have available. We are open right now. We do have programs you can join. We have guided tours, solar viewing programs, and our star parties 3 nights a week, Tuesday, Friday, and Saturday. And next month, we have our spring break activities. We'll be offering an expanded schedule for spring break. Need to make reservations too. We will highly recommend those for our programs. And we have education programs, astronomy field trips for students, our virtual visits. We'll be having teacher workshops coming up this summer. And you can support us. We're from the Friends of McDonald Observatory. We also have our online gift shop. You can also find out more information too. We'll post this on our various social media platforms. All right, so we hope you all enjoyed our program this evening. And thanks for tuning in. And we'll see you next time. And have a good evening and clear skies. Thank you very much.
Thanks for joining us. And thanks again, Stephen, for the awesome views.
All right.
Thank you,
thanks. Good night, everyone.
Yeah, and hopefully Stephen will not have to stay at the telescope due to the wind.
Yes.
Oh, yeah, getting home is going to be interesting.
All right. Have a good night, everyone.